This video will be about the Nobel Prize in Physics for the year 1910, awarded to Johannes van Waals for his work on the equation of the state for gases and liquids, and we will look today at his Nobel Prize lecture, which is summarized by me, and which is about a continuation of the work of the scientists you see here, Diderik Boyle and Charles Avogadro, who also worked on gases, and they formulated this law, the general gas law. Pressure times volume divided by temperature and the number of molecules, it gives a constant. Yeah, you see another. This is the graph. If you follow that law, and you see Van der Waals corrected that based, of course, on observations, experiments. The equation of state for gases and liquids is the subject. Well, here we go. Summarized by me, of course. In reality, it is a longer. Theoretical studies on liquids. In 1857, I read Claudius' treatise on the nature of motion we call heat. Gases seems material point moving at high velocity. Velocity is in the order of the square root of the absolute temperature. Maxwell gave a law for the distribution of these velocities, and Boltzmann proved it to be correct. I saw that when the volume of the gas is very much reduced, it can be made into a gas. There is no real difference between a gas and a liquid. There is the other states of aggregation too. There are two reasons gases do not comply with Boyle's law. First, the attraction between the particles, which was neglected in that law, and their proper volume, but was also neglected by Boyle's law. A had to be effect B, which is 4 times the value of the molecule in the gas, but it falls with the decreased external volume to a half. The other effect was more difficult. This was done. I use formula A. We will see that shortly. The work on the other formula was done by Korteweg, Lorentz, Boltzmann, Jeans, Van Laar, my son, and Koolstam. Boltzmann showed formula A to be inadequate, and Koolstam proved the formula had to be more complex. Van Laar did a lot of calculations to determine the constants, alpha and beta. This prevented me from getting further. The real reason for the non-compliance of real phases and liquids to Boyle's law, the situation is somewhat better. Using Laplace capillary theory, I reduced the mutation attraction of the volumes to a surface force, which the external pressure holds the molecules together. Laplace saw liquids as a continuum, and he was unaware of the molecules. I would therefore be incorrect to reduce the attractive forces to a surface force if the molecules are stationary, but they are moving. Thus, not every point in space is filled, but continuously filled in a mean, what they call the normal density. These considerations brought me to formula B. We will see it shortly, and I never expected the formula with A and B. These are constants assigned to be a constant value to be in agreement with all possible elements. I always said V is a barrel, quoting a series of values from Andrews. Perhaps the reason why B is rarely seen as a variable may be found in the way I calculated. At first I had to assume B was a constant, but later I found that it was a mistake. To determine the critical volume when B changes, the differential quotients dB divided by dV and d squared B divided by d squared V also need to be known. To determine the critical volume obtained the equation C. We'll see these equations later on. When we neglect these two differential quotients, Vk is 3b. This is a weak point in the theory. We cannot calculate the critical volume accurately. Using approximate formula for B, I was able to calculate that its Vk is about 2.2 mpg. I feared that would lead to a large deviation of the critical value, and we'll shoot the volume D, but this is not the case. I was able to conclude from the results of Sidney Young's experiments of the volume of coexisting vapor and the liquid phases on the saturation pressure level at various temperature. He determined the value with formula D at the critical point as 1 divided by 3.77 if P and T are the same values in my theory, and B is 3 divided by 8. The difference is due wholly to the volume. The critical volume is not 3 times Bg, but 3 times divided by 2 Bg, and Bg is about 2.125. The product pressure times volume divided by Ribera constant times the temperature is not 3 divided by 8, but 3 divided by 8 times the square root of 2. For the volume of T divided by P and dP divided by dt, minus 1, my equation gave A divided by V squared. Young's experiment gave 6 for this. For P is A divided by 6 times V as a volume in squared, with Vk is 3 divided by dPg. The volume pK is already 1.7 divided by 27 times A divided by Bg squared, and is count for pK. I have returned to this equation later several times. Already in 1873, I recognized that A and B might be vary with temperature and closely assumed A to be inverse proportional to the absolute temperature, leading him to the equation T divided by P times dP divided by dt minus 1 is 6, but only the half was found when A and B were kept constants. This value does not arise from a change in temperature, but from a change in B with volume. And then try to find whether if only B is a variable, this might be enough. Remaining discrepancies might appear if A and B vary with temperature. Faraday took this up in 1917, and I used the Clapeyron principle with only B varying with T and not with A. And A as a constant. This led to the next equations in 3 variables. Sidney Young, we will see this equation later. Sidney Young were determined accurately for a series of substances, but is the temperature are only a function of T. The temperature, as the temperature decreases, the value of the left-hand side of the equation increases very rapidly at first and then at an imperceptible rate. The experiment as far as T divided by T, dk, the critical temperature, is 2/3. At the right-hand side, increase to 1.4, approaching asymptotically to the value 1.5. The value of the right-hand side is represented by the empirical formula with T divided by dk is m. I investigated whether A and B being temperature dependent could correct for the increase of the right hand side. So the temperature was found to contain the square root of 1 minus m, but above the critical temperature this would give an imaginary value for A and B. Thus something had to be added, namely that the molecules associate to form large complexes. I call that cell association to differentiate it from chemical association. The examination is incomplete and now assume that large numbers of single molecules form a new group as a larger unit in molecular motion. What is the origin of the pseudo-association? Already in 1873, I concluded that the attraction of the molecules decreases extremely quickly with distance. Only the collision are responsible for the exhibiting of attraction. The Bay made a remark implying Boltzmann had predicted the formulation of the pseudo-association. Chemical association occurs when molecules form double molecules. The pseudo-association is due to normal molecular forces. It also leads to a surface pressure, although a low one. This was precisely how I assumed in my calculations. Then I quote, let the number of molecules that have been combined into a complex be so large that it is possible to speak of a molecule at the center surrounded by a single layer containing almost as many molecules as is possible simultaneously. Then, for the surrounding molecules, the attraction directed towards the interior acts only to maintain the complex, and this part of its attraction is lost for the surface pressure. Only the forces acting outwards from these molecules can contribute to the formation of the internal pressure, but of course for pseudo-association, as for true association, the number of formed complexes increases with decreasing temperature and volume. At the critical point, so I was compelled to conclude only a very part of the weight is presented as complexes. Then there are two types or more of molecules, simple and complex, n-fold. All values n may be possible. They seek for the laws of distribution of these values. I studied binary mixtures years earlier and published a theory in 1890. Boschat translated it from Dutch to French, and Korteweg studied the mathematical properties. I asked myself, did not have the study of the equation of state to be completed before applying it to mixtures. But the study of values of A and B had given results, so I applied it to mixtures, finding values for A and B again. Gibbs' treatise on the equilibrium of heterogeneous substances was helpful. Equilibrium sets in if the free energy is minimum from the temperature given and volume. I call the equilibrium surface of binary systems the psi surface. The phenomenon is not complex for a simple substance. For binary mixtures, it can become complicated, but in the end, it was qualitatively in agreement with my theories. Kuhn, Timmons, and Ullmann have experimented with binary system. Now looking back, I realized I have made detours. Maybe there is a deductive way it is indeed thought. Gibbs' elementary principles of statistical mechanics will be a guide. In the meantime, the law of corresponding states has become well known. This law has been instrumental in Dubois' determination of liquefying hydrogen and in Cameron Order's determination of the liquefying of helium. All kinds of other questions could have no place here, like Rigaud's club effect gas. General observation has to be made. In all my studies, I have been quite convinced of the real existence of molecules as actual bodies. Now we do not know the nature of a molecule consisting of a single chemical atom. Many of those who opposed the idea of being real bodies have been won over in the last decades. Great physicists like Boltzmann and Gibbs believe heat phenomena can be understood, starting with molecules. It's good to see many young physicists agree and find it an inspiration for the studies. Well, this is the summary of the lecture. In reality, it was longer. Summary is always shorter than the original, of course. If you want to read the original one, you have to follow these links, which will also be in the description under the video. For now, thank you for watching, and maybe until another time. Here you see, by the way, a graph for temperature and pressure for a gas. You see the triple point. Here's another. This is, in fact, this more or less the same graph, but then also containing pressure, temperature, and volume, so it's three-dimensional. You can see this if you come to Leiden, to the Boerhaven Museum. For now, again, thank you for watching, and maybe until another time. Next week, we will go to the year 1911.